Assalamualaikum. Jawab pas. Assalamualaikum dan salam sejahtera to my lecturer, which is Sir Azam. Today I'm going to present our case study presentation, which is study the Mitsubishi Lancer Evolution 6 Tommy McKinnon edition. So this is our group member. My name is Abang Amirul Kamim bin Abang Zakaria, and they are three members of us. Introduction. Vehicle dynamics is a branch of automotive engineering that focuses on how a vehicle responds to driver input under various conditions. It encompasses the study of force and motion in vehicles, especially in areas such as ride comfort, handling, and stability. Understanding vehicle dynamics is crucial in evaluating the safety performance and efficiency of a car. In this case study, a 2000 Mitsubishi Lancer is used as a subject vehicle to analyze and understand basic principles of vehicle dynamics in a real-world context.
My name is Esis Kasion and I will present about the objective of the case study. And the objective for our case study is by the end of the task, student will be able to first apply dynamics axle loads, second analyze driving and braking, second analyze aerodynamics, fourth apply perception of ride, fifth apply experimental measurement of adjusted gradient, and the last is apply cornering properties. Next, this is the vehicle data that we got from the brochure of the Mitsubishi Lancer that we use for our case study, and all the data from this vehicle data we use for the calculation of each question on the procedure. So for the calculation in question 1, the question is to figure out the load distribution on the axle when the vehicle accelerates from a standing start up uh, for 4% uphill road at 3.7 meter per second square, assuming the CG height is 0.5 meter. So this is the calculation that we use. We use the formula of static load, and then after got the answer, the value of C and B, we continue to do the formula acceleration with gradient condition.
And now is question number 2. And the question is determine the vehicle 1 until 4 gear friction force. And the second is traction limited acceleration if the coefficient of friction is 0.62. And this is a calculation. We use the formula is friction force. And the question 2 we use force. For the first gear, the answer is 14114.26 Newton, and for the gear 2 is 982.50 Newton. Also, the gear 3 is the answer is 7318.12 Newton, and the last is for gear. The answer is 554.47 Newton.
Okay, next is modification need to reduce aerodynamic drag and increase fuel economy. First is body design modification, streamline vehicle shape, teardrop-inspired design help reduce the drag coefficient. Next is camber tail design. This offers drag reduction while maintaining usable cargo space, commonly seen in hybrid vehicles. Next is underbody enhancement. Underbody paneling can flat panel minimize turbulence under the vehicle. Next is rear diffuser, improve aviation exit and reduce lift, contributing to better fuel to economy and high speed stability. Okay, next C, wheel and tire improvement. Wheel space and aero cover decrease air resistance around rotating wheel. Low rolling resistant tire. This can reduce friction, lending to improve energy efficiency. Last is material efficiency. Use lightweight composite material like carbon fiber, reduce vehicle mass and rolling resistance. Last is recommendation. Integrate real-time aerodynamic monitoring system to provide feedback on drag condition during driving and adopt aerodynamic while design and vented brake cover for a combined reduction in drag and brake cooling efficiency.
Okay, we're going to question number 4. Question is use tie data calculator and BND test source website to find tire stiffness and calculate suspension stiffness using K equal to 4 pi 2 M formula. Analyze the vehicle front and rear axle right rate and front and rear axle natural frequency in hertz. First, we use the website which is BND test source to find the tire stiffness, and after we find the tire stiffness we're going to use the formula given to find the suspension stiffness on rear and front. So that for the question 1, by using the data the given, you know that how the formula how to find the right rate is RR equal to KT multiplied by KS divided by KS KT plus KS. So we put the, um, the amount, then we calculate and we get the right rate for front axle is 268,363.62 Newton meter, and the right rate for rear axle is 118,601.97 Newton meter. So for the B question, the natural frequency for front is 4.579 Hz and rear axle natural frequency is 3.813 Hz.
So next, for the question number 5, the question is using an equipment geometry illustrations, determine the vehicle inside and outside steer angle. So before proceed the calculation, I do sketch the equipment geometry illustration, so it will easy to calculate later. And after that, we use the value on the brochure that in the vehicle data, and we got the value t equal to 1.51 meter, l which is the wheelbase is equal to 2510 millimeter, and I convert it to the meter and get the value to 0.51 meter, and the R equal to 5.6 meter. After that, we use the formula to find the outside and inside steer angle by use the formula outside steer then inverse tangent multiply to L divided by R and got the answer 24.53 53 for the inside steer, and the outside steer I got the answer 19.70 degree. So the explanation for the question 5 is the Acumen steering geometry is used to make sure that and four wheels of a vehicle follow the correct turning path during a turn. This helps reduce tire wear and improve handling, especially during low speed cornering. The steering angle for both the inside and outside were calculated based on the vehicle's wheelbase and track width. Track width. The result is like I mentioned before, and this value shows that the inside when turns more than the outside wheel, which is expected in Ackermann geometry. This difference in angles help the wheels point toward uncommon turning center located along the rear axle. The diagram supports this by showing the steering and aligned toward this center point. This confirms that the calculated angles follow the Ackermann principle and will help the vehicle from smoothing without causing the scrapping.
Okay, next is I will talk about advantage of tire change based on a review of a tire specification. First is improved grip and handling. Wider and softer compound tire increase surface contact, enhancing cornering and braking. The evidence is performance tire can reduce braking distance by 15 to 20% in dry condition. Second is increased safety. Seasonal or terrain specific tire, for example winter tire, improve performance in challenging condition. The evidence is winter tire improve cold weather stopping distance by 30 to 50% over standard all season tires. Number three is enhanced fuel efficiency. Low rolling resistance. Tire minimize energy loss, improving overall fuel consumption. The evidence is according to the U.S. Department of Energy, low rolling resistant tires can improve fuel economy by up to 4%. Last is application specific performance. Tailored tire choice support different driving environments such as off-road, racing, or touring, resulting in optimized performance. Okay, next is disadvantage. First, faster way and higher cost. Performance tires often have softer compound that wear quickly, increasing maintenance frequency. The evidence is lifespan can be reduced by up to 50% compared to standard tires. Second is reduced comfort and noise increase. Aggressive tread pattern or stiffer sidewall can lead to harsher ride quality and higher road noise. Number three is potential fitment and clearance issue. Larger or different profile tire may interfere with suspension or body component requiring further modification. Last is instrumentation error. Incorrect set tire sizing can alter the speedometer and odometer reading, affecting trip data and cruise control accuracy. Last is conclusion and recommendation. Tire chain offer measurable benefit in safety, performance, and efficiency when matched to the intended usage and environment. However, downsides such as cost and comfort must be considered. For recommendation, first is select tire that match both vehicle manufacturer specification and driving condition. For example, city performance and winter. Second is use low rolling resistant tire for daily commuting to improve mileage without sacrificing comfort. Last recommendation is rotate and inspect tire regularly to ensure optimal lifespan and safety regardless of type.
And next, discussion. How does the front rear axle load distribution of the 2000 Mitsubishi Lancer affect its handling, characteristics, braking performance, and cornering stability under various road conditions? And the answer is the other road distribution of 2000 Mitsubishi Lancer, a front engine, front wheel drive vehicle is naturally front blast. The configuration places more weight over the front axle, enhancing traction for driven wheel during acceleration. However, it can lead to understeer during cornering as the front tires are responsible for both steering and power delivery. Under braking, the weight shifts further forward, increasing the load on the front axle and improving braking performance, but potentially overloading to front tires is not properly balanced. A well-distributed load of side rear weight bears, as seen in performance vehicles, would after better dynamic balance, but the Lancer FF layered optimized cost, basking, and full efficiency over performance. And the next question is, what role does tractive force play in the acceleration performance of the Mitsubishi Lancer, and how does it vary with different road surface and divergent configuration? Tractive force is the force transmitted from the tires to the road surface, enabling acceleration. In the 2000 Mitsubishi Lancer, tractive force is primarily influenced by engine torque, gear ratios, tire grip, and weight distribution. Because it is a front-wheel drive vehicle, traction can be limited during hard acceleration due to weight transfer to the rear, reducing the normal force on the front tires. This can lead the this can lead to waste spin, especially on slippery surface. However, under moderate conditions, the Lancer delivers stable acceleration. It has seven limited slide differential or traction control system, if equipped, can be improved factor force delivery under varied conditions. And the next is, how does the aerodynamic profile of the 2000 Mitsubishi Lancer influence brake force, and what is its impact on fuel economy at different speeds? And the answer is aerodynamic brakes significantly affect the fuel economy of the Mitsubishi Lancer, especially at highway speed. The Lancer is relatively simple, boxy design compared to modern sedans, result in a higher drag coefficient, typically around 0.32 until to 0.34 for vehicles of its era. This means the engine must work harder to become air resistant at higher speed. Increasing fuel consumption modifications such as lower ride height, smaller underbody panels, and rear spoiler can reduce drag and slightly improve fuel efficiency. Efficient aerodynamic design reduce the energy required to maintain speed, which is critical for highway fuel economy. And the next, in what way do tire and suspension stiffness affect the ride comfort, road holding, and overall dynamic response of the Mitsubishi Lancer during various driving maneuvers? Tire and suspension stiffness directly impact ride comfort, handling, and responsiveness. In the 2000 Mitsubishi Lancer, OEM suspension tuning prioritizes comfort and basic handling for daily driving. Softer spring and dampers improve ride quality but can result in more body roll and less precious handling. Increasing suspension stiffness improves responses during cornering but may compromise comforts. Similarly, tire stiffness affected by sidewall hacks and construction play a role. Lower profile signal tire essence steering responses but transmit more road handset. The ideal setup balance both comfort and performance depending on the vehicle intended use.
The next discussion the next discussion is how does the Ackerman steering geometry implemented in the Mitsubishi Lancer contribute to cornering accuracy and minimize tire scrap during low speed turns. The Lancer employs Ackerman steering geometry to ensure that the inside wheels turn at a sharper angle than the outside wheel turn during a turn. This design reduces tire scrapping and improves low-speed maneuverability. Proper implementation of Ackermann geometry enhances cornering efficiency and reduces tire wear. In high-speed cornering, however, a more parallel steering geometry may be preferred to minimize slip angles, but for a compact sedan like the Lancer, the focus remains on urban drivability and tire longevity, making Ackermann geometry an ideal choice. Next discussion is how do the different tire specifications, size, tread pattern, and compound influence the traction, braking, and fuel efficiency of the Mitsubishi Lancer under both dry and wet conditions? The answer is the 225 for 5ZR17 tires used on the Mitsubishi Lancer are wider and lower in profile compared to the original stock tires. The wider size, 200 to 25 mm, gives better grip for cornering, braking, and acceleration. The lower sidewall, 45 aspect ratio, makes the steering more responsive and improves handling, but it can make the ride feel a bit stiffer on rough roads. The ZR rating means the tires are suitable for higher speeds, and the 17-inch rims give the car a sportier look and allow for better brake fitment. However, these tires are heavier and can slightly reduce fuel efficiency. Overall, this tire size improves performance and handling but trades off some comfort and fuel economy.
Okay, for conclusion. In conclusion, by preparing this case study, we all now can figure out how to find the load distribution when the data given to us is enough to find it. Besides, we also managed to calculate the tractive force for each gear ratio and also calculate the traction limited acceleration. Furthermore, we figure out what modification need to reduce aerodynamic drag of the vehicle and how to reduce vehicle fuel consumption. Next, we all figure out how to get the tire data using the tire information given and using the VND test source. Next, we also can determine the vehicle inside steer and outside steer angle by using an Ackermann geometry illustration. Lastly, we find out the advantage and disadvantage when the tire change to other size and different construction. Okay. This is the reference that we use to this case study. Oh, okay, that's all from us. Thank you. Terima kasih. Ponsiko,